Okay. Correct answer here is B. There it is. Okay. There's no other place. Current has to be the same. All right. So, follow-up question. Tell your neighbor. Okay. Would you be able to figure that same conclusion out if this is the way the equation is written on uh, the equation sheet? Okay. To simplify things, just say this. J times A. Okay. Sound good? Okay. Correct answer is A. Good? Okay. Current density all has to go through. So there's the denser, more current per cross-sectional area. A being that dimension there. Tell your neighbor.
No, because it's in the two. Second thing. That's good. I feel like eggs with the reason.
Correct answer is A. Okay, resistivity is a characteristic of the material. Okay, so here's your walkaway. Here's your takeaway. Oh, I think they have this equation. You don't even have to memorize it. I think they do. They do. They just put it like this. Electric field is equal to resistivity times J. Okay, so the higher the current density, the higher electric field. The higher electric field, the higher current density. Okay. Tell your neighbor. Correct answer is Slow down. Okay, think of a river. Skinny fast, deep, slow. Good? Okay. Yeah. Have a conversation. Correct answer is I like C. Crazy cats. Okay, this current density stays the same because current's the same and the area is the same. So whatever the ratio, like it's like as this increases, this also has to increase to keep this ratio constant. Good with that? Okay. All right, so here's the story of how this works. Um, here, okay, here in these moments while things are being established, there is a continual um, voltage. Let's see, how do we want to say this? In our, like, here's our positive plate, and here's our negative plate. And there is a continual electric, so this is positive, so it has a higher electric potential. I'm going to make up, say, 10 volts. This is 0 volts. So there's 10 volts across this plate. Okay. When these are connected, during the moments that's discharging, there is a continual electric potential drop across this wire as you traverse this. Okay. The slope of this is going to tell you your electric field going downhill. Okay with that? The electric field is constant throughout that. The electric field would also be constant across here if there was no flow. Well, actually, even with flow, but like this is just a momentary, within nanoseconds. Okay. This is in between the time where we just saw that video and the time this takes to discharge. Okay. So if we have this hooked up to a battery, okay, let's say we have a 10-volt battery. The electric field sets up here, so you get excess positive charges here. I don't really want to do all this. Red dots are positive. Okay, and blue dots. Let's see if I have blue. Blue dots are negative. Okay, the biggest difference happens across this point here. Okay, the electric field that is established, so the current throughout the whole thing is the same. Yes. Okay, the electric field. So right here you have a higher current density because it's skinnier. This is our resistor, by the way. Sorry. Okay, so the electric field. These are electric field lines. Goes out of positive. Electric field's going this way. Probably do it like that. Make it more. And this is after it's established itself. This is we have reached steady state. Good with that? Okay. So the electric field here is much higher. So like the current's the same. The current density when the area goes down, the current density goes up. And let's see what's on the equation sheet. The equation sheet says this electric field is equal to resistivity times. So as the current density goes up, so does your electric field. So electrons are zinging past here. Actually, this way. Faster here than in here. This is like a rapids. This is like deep river. Okay with that? So this is like on a hose, putting your thumb over the end of a hose. Like that's a resistor. That's a resistance. But water molecules are shooting fast past here. But the current here is the same as the current in the hose over here. Has to be. Otherwise, you get a bulge, like be blowing up like a water balloon. Does that make sense? Okay. So a resistor is going to cause a stronger electric field. Electrons are going faster, but the current's the same. You have a higher current density, and your electric potential. If you looked at your loop, okay, you've got the battery, which is the ladder, whatever the voltage is. We're going to assume that most of the voltage drop occurs across the resistor. Technically, some of that happens in the wire because there's a little bit of resistance. Okay, so some of the energy is lost, but most of that happens across that. And this demonstrates Kirchhoff's loop rule, voltage gain equals some of the voltage drops. Good with that? So that's what happens. Like, it's the best picture I can give you, bless you, what happens in a circuit and why it happens at a microscopic level. Good with that? I think I've pretty much beat that up. Everybody good with they go faster? Wait a minute. After leaving, sorry, it slows down. After leaving the resistor, it slows down. What? After leaving the resistor, compared to the speed of the electron before entering. Oh, sorry, good call. The same. Okay. The speed here compared to the speed there. And then before entering while traveling through the resistor. So be everybody good with A? Okay. Okay. Compare to the potential energy electron before.
Everybody's gonna claim that pencil. I'll take it. I'm out. This is my last pencil.
Okay. Electric potential energy. Tell your neighbor. Going to be less. Everybody good with that? Okay. I guess that's the end of the class. Do what? Yeah, I know. We'll do that tomorrow.
You don't want to do the conductive tape?
I do. We will. It just.
Can you assure us? I just want to look at it.
I'm working on lab or the test.